right, so today we're going to start chapter 2. Chapter 2 is kind of short, but it's a very strange chapter. In the beginning of the chapter, it's a little bit more algebra based. It is kind of weird. Today, actually, we're going to cover 3 sections because it's so goofy, and you'll see it as we kind of go. Okay, so we're going to cover 3 sections today. We're going to cover a section tomorrow. On Wednesday, we're going to review and take a quiz. And I know that seems really fast, but I think once you see what the material is, you're really, okay. Okay, this is honestly usually like the best quiz of the year. Then the second half of the chapter is starting to look at angle relationships. So we start like with linear pairs and vertical angles, and we build from there. Okay, so it's a very disjointed chapter. But the nice thing is it does go kind of quickly. There's a little project that's associated with this chapter towards the end. And we'll talk about that next week. But we'll be done with this chapter by Thursday. And that includes the project as well. Okay? Any questions as far as our plans? All right. So today we're going to talk about 3 things. We're going to talk about inductive reasoning, deductive reasoning, and something called finding the nth term, which you've actually done before. You just may not have called it that. Right? So here's the first part. The first part is about inductive reasoning. So inductive reasoning is the process of observing data, recognizing patterns, and making generalizations about those patterns. In geometry, we call these things conjectures. Okay, so conjecture is when you the generalization that you make when you use inductive reasoning. A lot of times in science, you call it a hypothesis. So geometry, they call it a conjecture. And then once you prove it, it becomes what's called a theorem. Okay, so after you prove it, it becomes a theorem. Okay, so after we prove it, it becomes a theorem. So here's an example. Can I change this? Here's an example of inductive reasoning. As a scientist dips a platinum wire into a solution containing salt, passes the wire over a flame, and observes that it produces an orange-yellow flame. She does this with many other solutions that contain salt, finding that they all produce an orange-yellow flame. So make a conjecture based on her findings. Make a conjecture about the flame. Anybody? Salt burns orange yellow, right? That's her conjecture. That's her hypothesis. Okay, that is an example of inductive reasoning. Does that make sense? All right. Here's another example of inductive reasoning that you see more on the math side. So if you consider this sequence, 2, 4, 7, 11. So let's make a conjecture about the rule that would allow us to find the next 3 terms, or to continue it, and then we're going to find the next 3 terms. So let's find the pattern here. What's our pattern? They go from 2 to 4, 4 to 7. This is adding 2. This would be adding 3, and then adding 4. So every time we're going to add, we're going to increase that step, right? Okay, so can we find the next 3 terms? Yep, so this time I'm going to add 5, and I'll get 16, good. Add 6, and I'm going to get 22. Add 7, I'm going to get 29. So this is inductive reasoning that you typically see in a math class. Again, you've done this before, right? You just maybe didn't have a title or a name with it. All right, last example of inductive reasoning. In geometry, sometimes we do inductive reasoning with shapes and patterns. Okay, so look at the following figures. Use inductive reasoning to make a conjecture about the next figure, and then sketch it. Okay, so this would be figure number 1. This is figure number 2. This is figure number 3. So on your paper, I want you to sketch figure 4. What would it look like? Okay, so go ahead and do that for a second. Have enough time to sketch that figure? Okay, what area would be colored blue? The bottom left? Right here? Is that okay? All right, so then what would the 14th figure look like? Wait, let me do. So if it goes 1, 2, 3, 4, it would loop back to 1, right? So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is what step 14 would look like. Is that all right? Okay, so this is inductive reasoning. That's one section. Okay, that was the first section in chapter 2. We good with that? All right, so next we're going to talk about deductive reasoning. Okay, deductive reasoning is showing the process of showing that certain statements follow logically from agreed upon assumptions and proven facts. So you're trying to convince somebody you're right. It's kind of like what a lawyer do. What a lawyer does. Sorry, it's Monday morning. What a lawyer does. Okay, so they stand in front of the jury. Ladies and gentlemen of the jury, my client is innocent because on this date they were here and they were doing this, and then they did this, and then they did this. They laid out their argument, right? That's what a lawyer does. That's deductive reasoning, where you're trying to convince somebody that you're right, and you keep making logical statements over and over again. You do this with your parents all the time. Mom, can I stay out until 10 o'clock tonight? Her answer, her question should be, well, if she doesn't just say no, she might say something like, well, why? Like, well, the movie doesn't get over until 8:30. And then we wanted to go get pizza. That might take until 9:30. And then I have to take so-and-so and so-and-so home. So that might take until 10. So then I might not get home until 10:15. Okay, that's an argument of why you need something to happen, right? Okay, deductive reasoning. A way we use deductive reasoning, you've done in the past, is kind of with solving equations. Okay, so you actually used to write algebraic proofs at one point, and we're going to talk about that a little bit today. It's just an example of deductive reasoning. All right, so if we start with this equation here, I want to go through the process of how do I solve it. So what would you do first to solve this? Distribute? Okay, so I'd end up with 6x plus 3. I'm going to distribute again, right? Plus 4x plus 2 plus 7 equals 42 minus 5x. Do you remember the name of the property that allows us to do that? The distributive property. So I can tell you, I know I can do that because the distributive property tells me so. Okay, what would you do next? Combine my like terms. So I'm going to combine all my x's on the left, so I have 10x. Combine my constants, I have 12. We just combined our like terms. I'm going to write CLT because every once in a while when we do proofs, we'll do geometric proofs. Sometimes we have to do combined like terms, and I don't want to write out combined like terms. You are welcome to, but I will always write CLT. In math, we don't want to write any more than we have to, right? Especially not words. Numbers are okay. All right, so now algebraically, what would you do? Add 5x. If I add 5x, I'm going to have 15x plus 12 equals 42. What allows me to add the same thing to both sides of an equal sign? Both sides of the equation. It's going way back. The addition property of equality. Remember that? Is that ringing a bell? That says you can add the same thing to both sides, or be like the subtraction property of equality if we're subtracting, multiplication property of equality. Okay, so this is the addition property of equality. Okay, we always write POE, property of equality. Because again, I don't want to write it out. You're welcome to. Okay, now what would I do? Subtract 12. So I have 15x equals 30. What allows me to subtract the same value from both sides? The subtraction property of equality. And now how would I solve? Divide by 15, you get x equals 2. What allowed you to divide both sides by 15? The division property of equality. Okay, that's deductive reasoning. Justifying your steps every time you make a statement. We do this a lot. Like chapters 4, 5, and 6. We do this a lot. Deductive reasoning. It is something that you're not good at first, but you get better as you go. Questions about this? All right, this is section 2. See why I'm combining things because it's goofy and short. Weird. All right, so now we're going to do what's called finding the nth term. Okay, finding the nth term. So consider that sequence there: 28, 27, 34, 41, 48, 55. Take a minute here. I want you to find the next 3 terms. So find the next 3 terms in there. Okay, what's the pattern? What's happening? Adding 7 every time, right? So if I added 7 to 55, I would get 62, add 7 more, add 7 more, 76. Not bad, right? That was back to our inductive reasoning. But what if I said, what would be the 200th term? We could probably figure it out, right? I would goof it up because I'd be bored. Right, and I would miscount eventually, or I'd lose count of where I was in terms of is this 200th term or not, and I would just not do it because it's too tedious. But there's a better way to do it, and that's what we're going to talk about. And this is what will probably be familiar to you, maybe just not thinking about it in terms of what's called the nth term. So we're going to come up with a function rule. So in the past, I think you've probably called it a function rule. To write an equation, basically a function, so that we can plug in that I want the 200th value and it spits out the answer for me. Okay, so here's how it works. Everything we're going to do today is going to be linear, and we're going to talk tomorrow about if it's linear or not linear. Excuse me. But think about slope-intercept form of a line, right? If this is going to be my function rule, we know n is slope, we know b is the y-intercept. Slope is just about change, how the line is changing over time, right? Okay. The y-intercept is a 0 term. It's where x equals 0. It's where it's crossing that y-axis. Okay, so keep that in the back of your mind for a second. So these are the numbers again, the exact same numbers. You told me that it increased by 7 every single time, right? Okay, that's change. That's how it's changing, that slope. So my slope is going to be equal to 7. Now I need the 0 term. I need the b value. I need that y-intercept. So let's use some logic here. Let's do some inductive reasoning to work backwards. I need to find when x is 0. I need the 0 term. Okay, so instead of, what did I have to add 7 to in order to get 20? 13. So my b value is 13. So now I can write a function rule. So the function of n, so f of n, or you could use x, it doesn't really matter. A lot of times in geometry, we use n when we're talking about this stuff because we call it the nth term. So f of n equals, I would have 7x plus 13. We're just putting it in slope-intercept form. So my nth term, what's called the nth term, is really just my function rule. Okay, it's really, oh, I should have put an n here, I'm sorry. It's really just my function rule. Now I can find the 200th term. Okay, now I can find f of 200. So I can take 7 times 200 and then add 13. I didn't look myself a lot from there, sorry. Supposed to be a 13 there. So 7 times 200 gives me 1,400. Add 13 more, so it's 1,413. Does this look all familiar to you? Except for maybe calling it the nth term? Yes? No one get me so? All right, let's do one more example. Okay, so if I give you this pattern, 7, 2, -3, -8, -13, -18. Unless they say otherwise, this will be our first term, our second term, third, fourth, fifth, sixth term. Okay, so you can make it a table if you want. We want to find the nth term, and we want to find, oh, it just says find the nth term. So we just want to find the nth term. So reading left to right, how is it changing every time? It's going down by 5 every time, so -5. Is that okay? So my slope is 5, -5, I'm sorry, my slope is -5. I also now need to work backwards to find my 0 term. So what did they have to subtract 5 from in order to get 7? 12, so my b value is 12. So f of n is equal to what? -5 n or x, whichever you'd like to use, plus 12. Is that okay? So that's the third section. That's why it's like, it seemed real goofy. All right. So I'm going to hand out the worksheet for your homework.